All right. So, hey, Chris, how are you doing? Hey, Doctor.
Doing well. Thank you for the invitation to be here.
Yes. So, tell us more about who you are.
Yeah, so I'm an associate professor of aerospace and mechanical engineering at NC State University. I've been at NC State since 2018. Excuse me. I was at UNC Charlotte before that, and starting in 2014. Just to go back a little bit, I graduated from University of Michigan. Both my undergrad and my PhD were from University of Michigan, the master's as well. In aerospace and mechanical engineering for my undergrad, I studied control systems through the electrical engineering program for my master's and my PhD work. At that time, when I was a researcher at Michigan, and shortly thereafter, my work was focused actually on automotive powertrain control systems. But I still had a passion for the aerospace industry, and I had a passion for not only control systems, which was what the emphasis of my PhD work was, but also aeronautics. I was fortunate enough to get an offer to work as actually the first employee at a startup company out of Boston for 3 years after that. And maybe I'll have a chance to talk a little bit about that company and how they've evolved. Alteros, by the way, is the name of that company. And then went into academia after that. And so that's where I founded a lab called the Control and Optimization for Renewables and Energy Efficiency Lab, or the CORE Lab for short. And so we focus on energy harvesting devices, particularly renewable energy harvesting devices, and improving energy efficiency for devices both in the air, underwater, and also on the ground. And we focus largely on control systems aspects of those devices. And we're involved in a lot of exciting projects now, many of which touch upon the aerospace industry. I'm excited to talk about them with you today.
Mhm. So, why do you want to become an aerospace engineer?
So if I go back to when I grew up, I can cite a couple of key events, I think, that triggered my interest in aerospace engineering and engineering in particular. One of those was, I remember the first time that I went with my family to Disney World. My family had noted that I was a lot more excited actually about the plane rides there than I was about any of the attractions or the Disney cruise that we went on when we were there. And subsequent to that, not only was I excited about the plane rides there, but I learned everything that I could about how airplanes work. This was at the age of 6, and so I didn't have a whole lot of advanced calculus or some of the prerequisites needed to understand all of the physics of flight. But I was able to learn about some of the basic forces and moments of flight control surfaces, and also some of the performance capabilities of aircraft, both commercial aircraft and military aircraft, in terms of their flight capabilities or speed capabilities. I learned all about. I learned not only about capabilities of aircraft, but also air traffic control system, and just how many flights were being orchestrated on a daily basis into and out of hub cities. And so, I would say that my interest in aviation after that first trip to Disney World probably took on a lot more technical interest, took on a much more technical level of detail than most 6-year-olds probably. And it was sort of with that intricate level of detail, I would always approach any new point of interest with a very intricate level of detail. Similarly, when my family would go on sailing trips as a kid, I very quickly learned about the points of sail of a boat, learned how to read charts, learned how to navigate, and was doing a lot of the work on a boat even at a relatively early age. Again, became very engaged at a very detailed level in an engineered system. In this case, a system that sort of combines the wind, an aeronautical phenomenon, with the water, so with the marine engineering flavor, if you will. Got very interested in space travel and learning about the planets and learning about how exactly orbits work and how exactly the orbital mechanics of launching a satellite into orbit work. In fact, I got so interested in space systems that there were a couple of instances when I was a kid where the teacher would have me present for a couple of the science classes, all the stuff that I had learned about the planets and about the solar system. And so all of these experiences made me realize that getting into engineering, more particularly aerospace engineering, was the right fit for me.
All right. So as you already mentioned, and I've gone through some of your bio, you focus on application of problem-solving tools in renewable energy. Can you tell us more about how that could affect aerospace industry?
Sure. Well, our lab focuses on a number of systems, a number of renewable energy systems. And as I mentioned, some of those systems are airborne systems, in fact, wind energy systems in particular. Other systems are ground-based systems, and other systems are underwater systems. Probably the system that is most relevant to the aerospace field that our lab is heavily involved in is what's called an airborne wind energy system. And the idea of an airborne wind energy system is it's a variant of a wind energy system or a wind turbine where the tower is replaced with tethers and what we call a lifting body. That lifting body can be a rigid wing, can be a fabric kite, it can be an aerostat. We've actually looked at all of those variants. But the idea is that by replacing that large steel tower with a tether or tethers, you can access much higher altitudes than you would be able to access otherwise, where the wind is stronger and is more consistent. Additionally, if you take a high lift wing, you can fly that wing perpendicular to the flow field, either in figure-8 patterns or elliptical flight patterns. And we discussed this in a lot of papers out of our lab, and a lot of our, we discussed this at some length on the webpage as well. You can fly that at speeds much faster than the prevailing wind speed. And what that means is that you can generate a given amount of power with a much, much smaller turbine and significantly less material. We're talking more than an order of magnitude less material than would be required by a traditional wind energy system. So that's one aerospace application of renewable energy systems where we merge concepts from wind energy with concepts from aeronautics and flight control. And so we're very heavily involved in that. We're actually pretty involved as well in the counterpart to that system, which is tethered marine hydrokinetic energy systems. So instead of harvesting wind with a tethered device, now we harvest ocean currents or tidal flows with a tethered device where we tether to the seabed or to the floating platform. So we've got a couple of projects involved with that as well. And I would note that our renewable energy portfolio extends beyond just the aerospace field. Mm-hmm. So we've got a project that's involved with mission planning and control of ocean surface vessels that are propelled either by wind, so sailing drones, or by solar energy. And the challenge there is when you're powered by a renewable resource, that renewable resource is intermittent, and there's some unpredictability to that resource. And so understanding the statistics of that helps you to plan out a mission. But the benefit of a renewably powered surface vessel is that its range is unlimited, unlike traditional robotic systems. So we're involved with that. And I would note as well that we're involved in connected and autonomous vehicle control. So using autonomous vehicles and connected vehicles, which means that the vehicles are talking to other vehicles and the vehicles are talking to the infrastructure, using those to improve fuel economy. So that's not a renewable energy application per se, but it's an energy efficiency application that has tremendous societal potential just because of the amount of fuel that's consumed by non-autonomous vehicles today.
Mhm. So, what has been your toughest accomplishment so far in your field?
Yeah, so I would say to date, still the most challenging accomplishment has been my work at the startup company, what was a startup company at the time, we'll call it an early stage company now, Alteros Energies. So Alteros is a company that initially pioneered a lighter than air system for harvesting wind energy. Basically, they used a lighter than air shell to lift a horizontal axis turbine to very high altitudes. So I was part of the early stages of that company. As I mentioned earlier, I was the first full-time employee at Alteros. And within less than a year of me joining the company, we designed, developed the control system and the instrumentation system for, and prototyped a fairly large scale version of that airborne wind system, which we deployed out of the Loring Air Force Base in Loring, Maine, up at the northern tip of Maine. And so that was a very significant effort, very multidisciplinary. My expertise is in control, but this required dynamic modeling, it required instrumentation, it required aerodynamics know-how, and it required a lot of teamwork with a relatively small but very, very bright team to pull this off. The company Alteros is still in operation. They pivoted more toward telecommunications for rural areas, basically using that lighter than air platform as a really tall cell tower. And I'm still involved in that company as a technical advisor, but pulling off that design, build, and test operation in such a short period of time with a relatively small budget, because it was a very early stage company at the time, was, I would say, still the most challenging accomplishment of my career yet.
All right. So, in the future, what is in your research, what is a big milestone that you're looking forward to?
Well, so we actually have a couple of big projects now that involve tethered systems for harvesting marine hydrokinetic energy. And these systems, unlike the Alteros system that I worked on before, they feature a very high lift to drag wing that's able to execute flight patterns, like I was describing before, perpendicular to the flow field. And if those flight patterns are executed robustly and successfully, you can generate an order of magnitude more power per unit of mass and also per unit of turbine area than you would be able to with a stationary system. So one of the most exciting projects that I'm involved in actually involves using one of these systems, we call it an underwater kite system, to provide power to an autonomous underwater vehicle. So the idea is the autonomous underwater vehicle, the AUV, will carry out its mission. At some point, it will park itself on the seabed, deploy the kite. The kite will harvest energy from the ambient flow to recharge the batteries on board. Then the AUV retracts its kite, continues on with its mission. Now, obviously, this requires the technical maturity of the technology that we're developing in the lab that's significantly above where it started. And we're slowly progressing to that level of maturity. So we are, as of now, doing pool-based tow testing of our setup. We're going to be moving into open water testing, controlled open water testing in the fall. And within a couple of years, if this project is successful, we'll actually be able to deploy a demonstration off of an AUV. Now, I can't say a whole lot more about it just because that's part of a defense project.
I see.
I can say what I've already said, but there are certainly some very exciting times ahead on that project if it's successful. And again, this is an underwater project, so it's a little different than an aerospace project, but the principles of that figure eight flight perpendicular to the prevailing flow are the same principles that are used for airborne wind energy systems to harvest an order of magnitude more power per unit mass through careful control and a well-designed aerodynamic device.
Right, because tides are just flowing water, flowing currents of water, and winds are just air flowing through the air. So
yeah, so the principle is the same. Now, I will say there are some practical differences between the two. One being that tides tend to be fairly predictable compared to winds. So you have a well-defined tidal period. You have a pretty good idea of what the maximum tidal flow speed is going to be. There's certainly weather impacts that a little bit, but it's not like wind where it can be really, really challenging, even hours in advance, to predict wind. And certainly wind doesn't typically follow the sort of cyclic variation that the tides follow. But the principle of operation of a tidal turbine system and a wind energy system, whether it's tethered or towered, is the same principle of operation.
So what is something that you regret not doing in your career?
Well, I've been fortunate, particularly attending University of Michigan and working where I've worked afterwards, to have access to a lot of really great resources in terms of seminars, in terms of professors that I've been able to interact with, in terms of labs that I've had the opportunity to get involved with. And certainly I've leveraged some of those resources, but if I had a chance to go back and do it again, I would much more aggressively leverage those resources, attend every seminar that I could attend, reach out to faculty about participating in summer research opportunities where I maybe was more hesitant to reach out before. I think one thing that's great now is that that you can be anywhere on the globe. I mean, I graduated undergraduate in 2004 and my PhD in 2009, and so certainly Google Scholar existed, and it was relatively easy to conduct a literature survey in your area of interest. But now you have easy access to TED Talks. You can be following the latest achievements of SpaceX. There are all these opportunities to participate in online webinars in aerospace that are far more pronounced than they were when I was a student, though they still exist. So I wish I would have gotten more heavily involved, and I think there's great opportunities for students, no matter where they're located, to become engaged with the community if they're proactive, just because of how many web resources there are out there, in addition to in-person resources if you're fortunate enough to be on a college campus, for example, with a vibrant aerospace program.
So on to that previous question about the milestone. What is after that milestone? What are we looking at? What's the future of your research? Where is it going to lead?
Well, I think that achievement of this milestone, even achievement of successful tow testing first in the pool and then in open water, really establishes our lab as a leader, perhaps the leader in the academic realm in marine hydrokinetic energy, tethered marine hydrokinetic energy systems, certainly within the US community. And so I would anticipate that that's going to lead to more research funding and larger projects, but additionally, there's some opportunities to spin off that technology. And so we're interested in the lab in not only publishing our research and keeping that research in the lab, but also establishing startup companies that can be led by students, very highly productive students, that can take that technology to the next level.
So also, what do you think is going to be the next biggest discovery in aerospace industry?
Well, I guess the notion of what kind
Hello?
But I think there are a few exciting innovations that are on the horizon. For example, private space travel, I think, is an exciting advancement that's on the horizon, maybe a bit on the horizon, but nevertheless, it's going to be an exciting advancement in the aerospace industry. I think that hypersonics and the potential for supersonic flight to come back in commercial venues has significant potential as well. I think some of the really exciting developments are on the space side of things, particularly now that we've transitioned into a largely private space industry, and just looking at some of the accomplishments from companies like SpaceX and Blue Origin over the last couple of years.
And lastly, what is your advice to high schoolers like me who want to become aerospace engineers to find success in this field of study?
Well, like I alluded to before, I said that I wish I had engaged more in terms of the opportunities that were available to me, in terms of seminars, in terms of TED Talks, in terms of but also you have the opportunity to follow leaders in the aerospace industry on Twitter, and then follow their updates. Follow closely SpaceX's updates as all of my students do. Really take advantage of all of the opportunities that are available to you to engage with the aerospace community, which includes both in-person and web-based opportunities. And I'm talking to someone who obviously has been very proactive in that, given that you're organizing this interview series, right? You're clearly engaging with professionals in the industry and with academics in the industry. You're reaching out, and I think that's a really, really good thing. You'll get a lot of viewpoints, and you'll make a lot of connections that way. I also encourage students to get involved in programs that supplement their technical education, like FIRST Robotics, for example, just being one of the that really gives you a hands-on exposure that complements your education really nicely as you take the next step, and you're filling out the college applications and hopefully trying to take the next step in your aerospace career, or just your engineering career in general.
Mm-hmm. All right. Well, yeah, that is the goal. My whole goal with this entire project is to, collect information from professionals and then give it to young people like me that also want to pursue some like aerospace engineering, and then build upon that. So yeah, that's the whole goal of my project. So thank you for coming out and supporting the project, and thank you for the interview. Thank you for presenting me the opportunity to interview you. And yeah, that's it.
All right. Well, thank you, and good luck. And I hope you get to talk to a really diverse and interesting range of
I think my internet just.
Oh. Well, I just said good luck, and keep doing what you're doing, and I hope you get a chance to interact with a lot of people who give you a really diverse and useful set of knowledge and advice.
Yes. All right.